Hello everyone. So today I'm going to present about constraint programming approaches in order to find the set of one-flip local optima in the context of quadratic unconstrained binary optimization. My name is Dr. Amit Verma, and I work at the Craig School of Business at Missouri Western State University. Um, so let's start. A little background about Cubo. And so Cubo has recently become a requirement for quantum annealers. And the optimization problem that we are trying to solve in Cubo can be represented by max x prime qx. Recall that the variables, the decision variables that are part of the Cubo formulation are binary decision variables. It has emerged as a very popular modeling framework, and you can find numerous applications of Cubo. And more recently, it has emerged into significant importance because of the rise of quantum annealers. Um, so, um, what we wanted to do in this research was look at an efficient way uh, to figure out a set of one flip local optima. And this is different from a typical optimization problem where we are interested in maximizing objective function. Herein, what we want to do is figure out a easy way to determine a set of one flip local optima and then use that set in some kind of search heuristic. So in order to achieve that, we would need to um, determine the properties of one flip local optima. So here are the properties for one flip local optima x hat for a maximization problem. Um, and so x hat is such that x prime hat q x hat is greater than equal to all its one flip neighbors. And what I mean by one flip neighbors is in this x hat, only one of these bits in x hat is flipped at a time. So in total there are n one flip neighbors if we assume that n is the size of the Q matrix. So here you can these equation is applicable for a maximization problem, and S1 indicates the set of all one flip neighbors, and there are n such one flip neighbors. Remember, we can utilize a similar framework for figuring out the set of two flip local optima, but then that will lead to its own complications because the size of the two flip neighborhood, it will be O(n) squared. Okay, so the one flip neighbor will be such that one of the bit is flipped and other bits are constant. So here if we assume that x hat is such that like the one of the neighbors of x hat is such that we only flip the ith bit. So here you can see that we took equation 1 and we are trying to break it down by using a combination of linear coefficient and quadratic coefficient, and we are also utilizing the fact that the one flip neighbor will only differ in the bit I. So you can see that here from with respect to the one flip neighbor, we have 1 minus xi hat, and then other bits are not flipped, so other bits stay at xj hat. So we can further simplify this expression for max xqx, and we can arrive at equation 3. So equation 3 will detail a much more simplified version of equation 2, and we can then take a look at equation 3 and then say that the properties of one flip local optima will be such that this expression given by qi plus some summation of qij xj hat. If that expression is greater than 0, then that specific bit in the one flip local optima will be 1, else that bit will be set to 0. So it's very easy to figure this out using a constraint programming engine like IBM CP solver, like Google's CP solver, and you can use this constraint programming setup to efficiently solve equation 3. The only challenge using equation 3 is it's a non-linear equation. So you have this quadratic coefficient xi hat xj hat, and we can use tricks from integer programming to further linearize this expression. So this is how we linearize it, and this lemma can be enforced by the following set of linear constraints. So now we have a much more efficient setup for a constraint programming engine, and you can feed these equations 4 and 5 into constraint programming engine using a penalty coefficient m for a maximization problem. Okay, I want to re-emphasize that the focus is on figuring out the set of one flip local optima efficiently, so that we can use the properties of that set as part of the search heuristic. Remember that there might be multiple one flip local optimas, and again, if there's only one flip local optima, that is guaranteed to be a global optima. So for one flip local optima, we are dealing with O2 and constraints because there are two constraints, two linearized constraints for each one flip neighbors, and then there are n one flip neighbors. If you move to analysis of two flip local optima, we need to handle on squared constraints. So that might be a complexity that you would like to think about. Here's an example based on equation 3. So if you are given this Q matrix here, you can translate this Q matrix into a set of set of constraints provided by equation 3. There are three constraints, one for each one flip neighbor, and then we can further linearize it and convert it into 6 constraints. One of this one flip local optima is given by 001, but as we mentioned, there might be like multiple one flip local optima, and once we have arrived at the set of this one flip local optima, we can then analyze the set and derive some properties based on the set. So this this constraint programming process using equation 4 and 5 is very efficient because these are just some linear constraints, and the IBM CP engine can quickly figure out a lot of these one flip local optimas, and this is what we will utilize in the next step that we proposed, which was a learning based heuristic. So we would like to analyze the set of one flip local optima and then try to make informed decisions based on that. So let's say that one of the bits was always set to 1 in this one flip local optima. That might mean that that bit is important. It's required to be set to 1, or it can mean the other way, but we can design a very clever learning based heuristic that incorporates a fact like that. We could also utilize this fact, this set of local optima in study of local optima networks. We can derive restart points, and we could use that in other heuristic settings like path relinking and taboo search. So we proposed a simple learning based heuristic that relies on the frequency of these variables. So how often were these variables set to 1 or 0 in that set of one flip local optima, and we store that information in this list frac 0 and frac 1. So frac 0 will store the chance of setting a variable xi to 0, again based on the set of one flip local optima that we obtained very efficiently. So let's say that out of these 10 one flip local optima, x1 was always set to 1. In that case, frac 0 for x1 is 0 and frac 1 for x1 is 1, because there's a 100% chance that that variable was set to 1. And again, we can use that for estimation. We can run like data analytics models based on this frequency setup. In our case, we simply designed a heuristic that uses this information by altering the linear coefficients of the existing Q matrix. So our purpose is to perturb the linear coefficients of the Q matrix such that using this information from the frequency set, we are forcing the solver to make decisions. So for instance, let's say we want to favor local optima and x1 was always set to 1 in the set of one flip local optima. Then what we will provide the solver is we'll provide a hint to the solver that maybe it's a good idea to set x1 to 1. So the way we provide that hint is by incrementing the linear coefficient corresponding to x1 for a maximization problem. But again, this is just a heuristic. We also have a heuristic where we escape local optima, where we give preference to escaping local optima, and that is achieved by a mirror image of the favoring heuristic. So now let's say x1 was set to 1. Now we will encourage the solver and say that maybe it's not a good idea setting x1 to 1. So we can make these slight perturbations to the linear coefficients of the Q matrix based on the numbers that we got from the frequency set. Remember that this analysis relies on two parameters, alpha and delta. So alpha can be regarded as a threshold. We experimented with 99% chance, 95% chance, and delta is that slight perturbation in terms of the maximum coefficient of the Q matrix. So for example, in our case, the maximum coefficient was 100. So in that case, we are just perturbing the Q matrix slightly. Again, these are hints. These are soft constraints. These are not hard constraints. We are not setting x1 equals 1. We're just incrementing or decrementing the linear coefficient corresponding to x1. As I mentioned before, these are some of the results that we got from our routine. First, like the properties of the one flip local optima, we realized that the set of one flip local optima is highly diverse compared to a traditional greedy heuristic. And again, the emphasis was on the search for that set, so that is slightly different, and that is why you see that the objective function behavior is not very good compared to the greedy search heuristic. But what we have observed is we can quickly figure out a diverse set of one flip local optima. We experimented with both favoring local optima and escaping local optima using Q1 and Q2, like again based on these slight perturbations. and we realized that it leads to improvement in solution quality in majority of the instances as indicated in this table. So you can figure out, okay, the objective function when we just used q and the objective function when we used q1 was different, and most of the times it was favorable to make these small perturbations. So in conclusion, we covered a constraint programming based approach and obtained a highly diverse set of local optima. We proposed a learning based heuristic that alters the linear coefficient corresponding to the Q matrix based on the frequency distribution obtained via the set of local optima. And then using that, we covered a heuristic where we make changes based on whether we want to favor the set of local optima or escape the set of local optima, and both these cases led to improvement in solution quality. So this is my contact information, and this is a link to the archive paper. Please let me know if you have any question. Thanks for your time.